introduced what is known as the concept of Lebesgue outer measure, which we denoted as M star, and for E subset of R, M star is defined as infimum over sum of the lengths of the intervals, such that E is contained in this union. That means these intervals, they cover E, and In is an open interval. For each NNN. Yes, so this is what we called it as the so-called Lebesgue outer measure. Okay, so we saw some of its properties. The main thing is that this was introduced to extend the notion of length, and we saw that M star of I is equal to length of I if I is an interval. And then one of the easy thing, but an important property of the Lebesgue outer measure, what is known as that this M star is translation invariant. Yes, so these are some of the things that we saw. Right. Now let's proceed. Today we are going to see what are known as the additivity properties. Well, so this Lebesgue outer measure is not additive, but it is subadditive. That is the main thing. Well, let's begin with the lemma. That first thing, that Lebesgue outer measure is finitely subadditive. That means what? That means if EK, if you have a finite collection, is any finite subcollection of sets, then M star of the union is less than or equal to the sum of the outer measures of the individual sets. Yes, so this is what is known as finitely additive. Right. Yeah. Proof. So first thing that you'll have to observe, that it is enough to prove for n equal to 2. Why? What will happen for the general case? Follows from
Induction.
Yes, right, exactly. Follows from induction. As the general case follows from induction. Yeah, so this is one of the standard things that we are going to do again and again. Whenever there is a need for proving for n sets, we'll prove it only for 2, and then the general case follows from induction, right? So let E and F be any two subsets of R. If one of them if one of the two sets, sorry, if one of the two sets, if one of the two sets have infinite Lebesgue outer measure, then we are done. So there is nothing to prove. Right, because the statement is trivially true, therefore we are done. So therefore, we shall assume that both sets, both the sets E and F have finite Lebesgue outer measure. Right. So as usual, we'll start with our familiar one. So start with an epsilon positive. So once you have an epsilon positive, then there exists countable collections from the definition of the Lebesgue outer measure, what I am writing now. Yeah, so because m star of E is the infimum, what is m star of E plus epsilon? What can you say about m star of E plus epsilon for any epsilon positive?
That will not a lower bound.
Can you be more specific? Yes, that is not even a lower bound. That's right. Very good. Right. It is not only that it's an infimum, it is not even a lower bound. Therefore,
There exist some elements in E which are not being covered by the collection of intervals.
What are we looking? Infimum is taken over what?
The sum of lengths of interval.
Lengths of the open intervals such that this collection of intervals they cover E. Which means that m star of E plus, once you have an epsilon, then m star of E plus epsilon is not an infimum, and therefore you get at least one cover of open intervals whose sum of the lengths of the individual intervals is less than or equal to m star of E plus epsilon, right?
Yes, sir.
So that's what we are going to write. There exist countable collections Ik and Jk of open intervals such that E is contained in union over K in an IK, summation over K length of IK is less than M star of E plus epsilon by 2. And similarly, F is contained in union over K in N JK and summation over K length of JK is less than M star of E plus epsilon by 2. Each one of them. Right. So now note that the countable collection
So shouldn't that be M star F plus epsilon by 2?
epsilon by
M star F.
thank you. It should be right. Second one is for F. Thank you. Yeah, thank you. The countable collection IK union with JK. Yeah, this countable collection covers E union F, right? And therefore, from the definition of the M star of E union F is less than or equal to summation over K in N length of IK plus summation over K in N length of JK. Right? This is from the definition M star. But then just now we have chosen. How did we choose these IKs and JKs? Such that this is less than, well, you can even have an equality, it doesn't matter. No, you will not have, doesn't matter. You will, no, I don't know. So this is less than M star of E plus M star of F plus epsilon. Now epsilon is arbitrary. We have M star of E union F is less than or equal to M star E plus M star F. That's it. Fine. So this is only for finite number of sets. Natural question is, if what happens if we choose infinite, that is countably infinite? Yes, the same thing actually holds. Lebesgue outer measure is countably subadditive. That is, if EK.
Sir,
Ah,
let us suppose, sir, in alias of E, we take minus.
Vicky. Hello, Vicky.
And am I audible, sir?
Yes, you are audible, please.
Sir, my question is, suppose in with set E is taken minus infinity to 0.
Right.
and set f is taken to 0 to infinity, then
Right.
in this case outer measure of E is infinity and outer measure of also infinity.
Yes. So that is the reason we have first written. If any one of the two sets have infinite Lebesgue outer measure, even if one of them have infinite Lebesgue outer measure, then there is nothing to prove. The statement follows trivially.
So sir, actually I am asking how we compare infinity.
So okay, so you wanted the okay. So this is what you expect, right? Maybe let me write down. So infinity plus infinity is infinity. This is infinity calculus. Infinity plus any number, finite number is again infinity. Any finite number minus infinity is going to be minus infinity. Infinity times infinity is again infinity. Infinity minus infinity, this is undefined. So this is one of the standard things that we used throughout this course. Is this what you expect, Vicky?
Okay sir, got it.
Right, for any finite number x, if you add infinity, it is going to be infinity. If you subtract minus infinity, if you subtract infinity, it's going to be minus infinity. So infinity minus infinity is undefined. Is countably subadditive, that is if Ek is a countable collection of subsets of R, then m star of union k equal to 1 to infinity Ek will be less than or equal to summation k running from 1 to infinity m star of Ek. Yes. So here we will have to prove it for infinite. We cannot reduce it. But as mentioned earlier, note that if one of the sets have one of the sets has if one of the sets have infinite Lebesgue outer measure, then even if one of them, then the statement is trivially true. Right. So we assume that all the sets have finite Lebesgue outer measure. Right. Fine. So let's recall what did we do there. Let's go back. How did we get into the, how did we do the proof? We started with an epsilon, and then for each set you got a countable collection with this property. Summation over k, length of ik is less than m star of e plus epsilon by 2. Right. Yes. Yes. How to do that here? How to do that here? How to do that here?
Maybe we can take epsilon by 2, then epsilon by 2 square, epsilon by 2.
Right, exactly right. Right, very good. So let epsilon greater than 0. For each k in n, there exists a countable collection ikn nnn of open intervals consisting of open intervals such that ek is going to be contained in union over nnn ikn and summation over nnn length of ikn is less than m star of ek plus epsilon upon 2 raised to the power k. Fine, this is what we are going to have. Now the same proof, whatever we did there, same thing. So you will have to observe that countable union of countable sets is countable. So as usual, note that the countable collection ikn k comma nnn covers union over k in n ek. Therefore, m star of the union is less than or equal to summation over k, summation over n, length of ikn. Yes. But then each of these is less than summation over n, length of ikn is less than m star of ek plus epsilon upon 2 raised to the power k. Now the summation over k, 1 upon 2 raised to the power k, that's exactly 1, and therefore this is going to be, maybe I'll put it in the next line. This is going to be summation over k n star of ek plus epsilon. The same thing. Since epsilon greater than 0 is arbitrary, we have m star of the union is less than or equal to summation over k m star of ek. Right. Fine. Now let's do some examples. We'll do one example and then we'll do a bit difficult example. Well, this you must have seen in real analysis, the so-called Cantar set. Yes, how do you construct the Cantar set? How do you construct the Cantar set?
We just remove the middle one-third part in each subinterval.
Can you repeat? Sorry.
We remove the middle one-third part in each subinterval.
Subinterval of?
0, 1. When we write 0, 1 to representation, we don't write numbers which contain 2 in their representation, which contain 1 in their representation.
Which doesn't have 1.
In their
Right?
representation.
When you give the ternary expansion, you are removing all those elements which doesn't have 1 in the expansion. Yes. Right. So let me repeat. So consider the unit interval, which I am calling it as C0, 0 to 1, and then you split it into 3 parts and then remove the middle one-third, 0 to 1 by 3, union with 2 by 3 to 1. Fine. And then split each one of these into 2 intervals into 3 equal subintervals. Remove the middle part. 0 to 1 by 9, union with 2 by 9 to 1 by 3, union with 2 by 3 to 7 by 9, union with 8 by 9 to 1. Again, keep doing this again and again. So I am just putting a dots. I'm just putting dots so that you know what to do. If you keep continuing, this, what do we obtain? We obtain a sequence Cn of subsets of 0, 1 such that, yes, first thing is that each Cn is compact. In fact, it is closed and bounded. And the second one is that Cn contains Cn plus 1. Right. So now let me call C as union over, sorry, other way, intersection over n in n, Cn. How do you know that this is non-empty? This is the way you construct the Cantar set, right? But how do you know that this is non-empty?
Cantor's intersection theorem.
Cantor's intersection theorem. By Cantor's intersection theorem, C is non-empty. Right. This non-empty set C is what is called as the Cantar set. Fine. Our aim is not to do this classical real analysis, but we are here for doing measure. So let's calculate. So what is m star of C1? What is m star of C1?
2 by 3.
1.
2 by 3. M star of C2. C2.
Sir,
4 by 9.
sir, n can be 0, na? Small n.
Well, it doesn't matter in this case. It doesn't matter.
So we have to mention it or not?
You don't have to. So that is not a big deal. Well, if you want, you can even have it as singleton 0. Doesn't matter. So that if you want, I can even add one more. Yes, what is m star of C2? 4 by 9. M star of C3. 8 by 27. Well, let me rewrite the whole thing, which is 2 by 3 power 0, 2 by 3 power 1, 2 by 3 square, 2 by 3 cube. Therefore, if I keep doing it, I will have m star of Cn to be 2 by 3 power n. Right? Therefore, m star of C, m star of C is contained, so C is contained in all Cn's, which is same as, so in fact, this by definition is m star of the intersection, which is less than or equal to, which is contained in Cn for all n. So this is less than or equal to m star of Cn. Right? What is m star of Cn? Which is 2 by 3 whole raised to the power n. That's it. 3 whole raised to the power n for all n in n. And where will this go to? 2 by 3 whole raised to the power n.
0.
0.
0, sir. 0.
Right. Therefore, m star of C is 0. The only possibility is that it should be 0. But what do we know about m star of C?
Sir, it can be countable set.
It can be
Countable set.
Is C a countable set?
No, sir.
Countable or uncountable?
Uncountable.
Uncountable.
Yes, sir.
Countable or uncountable?
Uncountable, sir.
Uncountable, sir.
Uncountable. Well, maybe I'll simply leave it as an exercise. Show that the Cantar set C is uncountable. Right. So this is, so you have an uncountable set. So this is an example for an uncountable set. having 0 Lebesgue outer measure. Right. Fine. Now let's proceed. Next example. So, well, we started with what is known as additivity. That's what we wanted. That's what the title says. We wanted to study, but what we have been looking at is that at most that we were able to prove is only that it is finitely subadditive and it is also countably subadditive. So what happens if I choose EKs to be pairwise disjoint? If I choose EKs to be pairwise disjoint, will I get an equality? Right, let's see if that is true or not. So in fact the answer is no. Yes, so here is an example. The example is a bit difficult, but still please spend some time on understanding. On R, define a relation tilde as follows. X is related to Y if and only if the difference x minus y is a rational number. Yes, so this is the relation. Here is an easy observation that this tilde is an equivalence relation. It's an equivalence relation. Yes, what is an equivalence relation?
Reflexive, symmetric, and transitive satisfied.
Yes, so any relation that is reflexive, symmetric, and transitive is called as an equivalence relation. Yes, start, verify it. I'll give you 2 minutes time. Please verify it. If you have verified, please raise your hand. Others, please. Others, again, let me repeat, please finish it. Right. So what is the property of the equivalence relation?
It partitions the set.
It partitions the set. In fact, right. So this is an equivalence relation. Hence, R is the disjoint union of equivalence classes. Right. Right. So now we want a set E. Let E be the subset of 0, 1 such that its intersection with each equivalence class is a singleton. So it is a subset of 0, 1. It's a subset of 0, 1, and if you take the intersection of that set with each and every equivalence class, it is going to be just a singleton. You'll have only one element at most. So how to get such a kind of set? So I'll just give hint. In fact, such a set exists by axiom of choice. What is axiom of choice? So in fact, so you apply axiom of choice on the collection this collection E equal to all those equivalence classes intersection with 0, 1 such that x belongs to 0, 1. Yes, which means you pick one element, only one from each one of them. Yes, so this is the thing. Right. Now things are quite easy. Having said this much, now if you have two elements from 0, 1 and if you have two elements x and y from the interval 0, 1 and if x is related to y, then the rational number because they are related to each other, the rational number x minus y is a rational number. Well, so let if x let r equal to x minus y then q. Right. Now what can you say about this r? What is the lower bound and upper bound for this r?
-1 to 1.
Lower bound is
-1.
Upper bound
1.
1. Then -1 less than or equal to or less than or equal to 1. So at most this is what you can expect. Right. Now what am I going to do is that I'm going to list all the rational numbers between -1 and 1. So let R1, R2 be an enumeration. Of the set of rationals in 0, 1. Right. Sorry, not in 0, 1. -1, 1. -1, 1. Right. Now I have a set E, and then so now let me call ENs as E plus Rn. Rn, NNN. Yes. So what we wanted is countable additivity, that is we wanted an equality. So, and we are expecting at least for pairwise disjoint sets. Right. So, well, the first claim here is that the collection En is pairwise disjoint. Right. Yeah. Proof. Well, it's quite easy here. So now you choose two things. Let n comma m belong to n with n not equal to m. Right. So suppose that En not equal to em. Sorry. Suppose that En intersection em is non-empty. So we'll have to come up with a contradiction. Fine. So then there exists x comma y in E such that because En it is given by E plus Rn while Em is given by E plus Rm, and therefore you get two elements x and y from E such that x plus Rn will be same as y plus Rm. Right. So that implies that x minus y, which will be Rm minus Rn, and Rm is a rational number, Rn is a rational number, and therefore this is the difference is a rational number, and which means that the difference x minus y is a rational number. That means this is equivalent to saying that x is related to y. Right. Now, since x comma y, they both come from E, and you can have at most only one element from an equivalence class, that implies that x equal to y. So that Rn equal to Rm, which is impossible because we have assumed that n is not equal to m. Right. Fine. Yeah, let me just take 2 more minutes so that I can finish this one. I don't have to repeat it next time. I'm sorry. Please. Yes, so next one. The next claim is that this m star of the union. Yes, so the lower bound is 1 and the upper bound is 3. Right. So first thing, is that E is contained in union of, sorry, 0, 1, and Rn, each Rn, it belongs to minus 1, 1. That's what we have done. And therefore, En, which is E plus Rn, which is going to be contained in, so at most you can expect is on the left hand side you can expect minus 1, on the right hand side you can expect 3 for all n in n. Sorry, wait, 3, 2. Right. So this is true for all n. So that implies that the union is contained in minus 1 to 2. Right. This is 1. On the other hand, notice that for each x in 0, 1, for each x in 0, 1, there exists y in E such that x is related to y. That is how we have defined. Well, sometimes this x can be same as y. Y can be same as x. That's a different thing. And therefore, thus x belongs to n for some m in n, n in n. Right? For some n in n, x belongs to en. Therefore, this 0, 1 is contained in the union. This is number 2. Therefore, from 1 and 2, what do we have? M star of 0, 1 is less than or equal to M star of the union, which is less than or equal to M star of minus 1, 2. That is 1 less than or equal to M star of the union less than or equal to 3. That's it. Fine. Now we will have to show that what we wanted fails. Well, so suppose that M star of the union is equal to summation over n in n M star of En. Now, what is En? En is E plus Rn for all n in n, and therefore M star of En is going to be M star of E, because M star is translation invariant for all n in n. Therefore, M star of the union is equal to summation over n in n M star of E. So this implies that 1 less than or equal to summation over n in n M star of E less than or equal to 3. Yes. So what can you say about this one? Can this happen? What does the left hand side tell you? See, if you have
M star is non-zero.
huh?
M star of E is non-zero.
M star of E is non-zero. Yes. So left hand side tells you that. So left hand side implies that M star of E is non-zero, while right hand side implies that n star of E should be 0. So see, if you have a fixed constant, either this is 0 or infinity. This is 0 if C is 0. If C is non-zero, then this is going to be infinite. Only these two are the only possible things. Right? And therefore, your left hand side says that it is non-zero. Right? And therefore, this series is infinite. But your right hand side says that it's a finite quantity. And therefore, the only possibility is that m star of E is 0. So, which is a contradiction. Therefore, m star of the union is not equal to summation over n n star of en. Yes, these two are not equal. That's the only thing. So let me stop here. Right. So it says that the Lebesgue outer measure need not be countably additive even for pairwise disjoint subsets. We'll see many things in the next class.
Sir,
Yes.
sir, can you go back to the Cantar example?
Here.
Yes, sir. So in this, how we are writing m star of Cn is equal to 2 by 3 raised to power n4 and greater than equal to 2. Because we only know Lebesgue outer measure is length of the interval when you have interval and it's subadditive, not additive. Should be
Length is
less than equal.
right. If you are very specific, then let me put it as a doesn't matter. If you are very specific, then let me put it as less than or equal to. Thank you. So here we will have, doesn't matter. Right? Fine.
Yes,
Still
sir.
the same. Whatever you want, whatever we wanted holds. Is that fine?
Yes, sir.
Yeah. Thank you.
Sir, so what is the outer measure of rational and irrational? Means set of rational numbers and set of irrational numbers.
This we did. What is the m star of the set of countable numbers? Any set of having countable number of elements.
That is
M star
the
of any set. So m star of any set having countable number of elements is 0. Which means the m star of set of rational numbers is 0. Clear?
What is rational?
Irrationals. That we will
Set
see.
of
Irrationals, right? That we will see. We haven't said anything as of now. So we will see something more. Fine? Yeah.
Okay.
Right. So, fine. Let me stop here. Thank you all.